Okay, so here we talk about the electric field due to a dipole. Yeah, due to a dipole. So here's the definition about electric dipole. In Chinese, it is called 电偶极. Okay, so here di means two, and the pole means d. Okay, so yeah, so it says an electric dipole consists of two particles with charges of equal magnitude q, but opposite sides. Okay, so with these two conditions, separated by a small distance e. Okay, so you can see on the right figure of this one. This one is a dipole. We have, or maybe this one is also a dipole. So you can see this charge. This is a positive charge with the charge amount of positive q, and another charge with negative q charge amount. So they have the same amount of charge but opposite sides, and they are separated by a small distance. We call it d here. And yeah, you may ask why it can be whole like that. Why don't it have some sort of yeah? Of course, when you talk about the Coulomb's law, you know, when you have two charges in opposite side, then there will be force attracting them. But yeah, but actually in the nature we have some electric dipole. For example, when you learn chemistry, high school chemistry, you of course know H2O. What is H2O? Is the water. Is the water molecule. And when you learn chemistry, you know the structure is something like you have O2 minus, and then you have H plus, 2H plus, and then there are something called the covalent bond, to really connect the ions together. Yeah, the hydrogen ions and also the oxygen ion. Okay, so during the chemistry class, there are something called the dipole, which means that it feels like it is like a negative charge plus a positive charge, something like that. But of course, it is not actually the same, but yeah, it is some sort of physical model, something like that. So this is the electric dipole, something like that. Okay, and then he tells you that between water molecule, then there may be a higher interaction between them, because there are something called a hydrogen bond or whatsoever. And okay, so yeah, so this is a shot of electric dipole in our daily life. And here, this is physics class, so we talk about the physics for the dipole rather than going through a different chemical material. Okay, so here we define another physical variable called the dipole moment. In Chinese, it is called 电偶矩. Okay, moment. So you can consider it something like the torque, something related to the torque. So in physics 1 or mechanical class, you should have know something like the torque 力矩. Okay, torque. Okay, yeah. So so this is a definition. P here, P is the dipole moment, and then Q is the charge amount, because as the definition of the electric dipole, it has the charge amount of Q. Of course, it has plus Q here and negative Q here. And here we reduce the positive value Q and then multiply by the distance D. So the total stuff is called dipole moment. And then, of course, the SI unit for the dipole moment will be this one. This one is the charge. So the SI unit is Coulomb. And then the SI unit for the distance is, of course, meter. So it is C times M, C times M. And one thing to know is that dipole moment is a vector. Dipole moment is a vector. Okay, and we know this one charge is a scalar. So here this distance vector is also a vector. This distance vector is also a vector. The definition of this distance vector is pointing from the negative charge to the positive charge. So the point, so D vector, for example, in this figure is from bottom to top, bottom to top. And of course, Q is a positive value, which means that P has the same direction as vector D. Okay, so this is the definition of the electric dipole and the electric dipole moment. Electric dipole moment. So the dipole is, it's this one. We have Q. Q is the charge amount for a single particle, and then we of course have another negative Q, and then the D is the distance. And when we consider this is a vector, then it is from the negative sign to negative charge to the positive charge. And then if we multiply them together, it is the dipole moment. Okay, so the magnitude of the E field set up by an electric dipole at the distance point on the axis can be derived as this expression. Of course, you may ask, why don't you cancel this 2 with this 4 so that it looks like 1/2 pi epsilon naught times a QD over Z cube. Usually, in mathematical class, you are required to do so. But here, as I mentioned, usually 1/4 pi epsilon naught is a constant occurs together. So maybe we can just regard it as a K times 2QD over C cube. Then we don't really cancel this 2 and this 4. Okay, so yeah, so of course this is the first expression. This is K, this is a constant 2, and then Q times D. Q times D, what we have defined is the dipole moment, so we can also write it as 2P over C cube. C cube means we try to connect these two charges, and then this axis is called the Z-axis here. This is the Z-axis, and of course the positive Z direction is from the negative charge to positive charge. Maybe you can just call this point is 0. This is 0, and then go to that side. I think in this figure the axis is defined like this. So because you can see here, Z is from the middle point of the dipole of the electric dipole to the point you concern. So which means that for this equation, it tells you the electric field generated by this dipole moment only on this Z-axis, and this Z means the distance from the point you concern to the middle point of the electric dipole. You may ask, how about the other points out of this Z-axis? I will say it is not easy to write a closed form, or the closed form does not look like a good form. So for this equation, we only show the E field on this Z-axis. if you really need to know the E field out of this z-axis, then probably you need to write a program, a computer program, or use some EM simulation software to do so. And of course, in the lecture or in the exam, you usually required to do some hand calculation. So yeah, only on the z-axis has good enough expression to show here. And of course, in the next page, we will show why the equation like this. In this lecture, I usually will tell you why the equation look like that and how to derive the equation if I really know. But yeah, and of course, I think more than 95% of the equation I will tell you how to derive. And if you can understand the mathematics, then it will be good for you. And if you can't really understand, then you just know how to apply the equation, it will be fine. Then yeah, during the exam, I will show you the formula. You don't need to remember too many formulas because I think in the whole semester we will learn quite a lot of formulas, but you don't really need to remember too much. If you can really understand the derivation, it will be good for you. Okay, so yeah, so here the equation, the E field generated by the magnetic dipole on the z-axis look like this, and here is a condition. It is called where z is the distance between the point and the center of the dipole, assuming z is much larger than d. Z is much larger than d. D is the distance between this one, and then the z is the distance from the point P you concern to the center, which means that this point is far away from the dipole. Usually, this dipole is a very tiny structure, like the water molecule, something like that. So you concern the E field generate far away from it. Okay, so in January, we can call it we can call this one the far field condition. Yeah, because when we talk about the E field near it, then it might be not so easy to consider. So we add this condition, the far field condition, as much as the z is much larger than d, then this expression will be a approximate solution, but it is accurate enough, maybe. But yeah, of course, you may ask, how large is z so that it is much larger than d? Of course, it's up to how accurate you want this equation to be. Sometimes maybe z is larger than 5d, or maybe z is larger than 10d, or it's up to how accurate you want it to be. Different formula might have different ranges, but yeah, if you want it to be more accurate, then you hope this z is as large as possible. Okay, so let's come back how to derive this equation. So on the right figure, we can see this is the positive charge, this is the negative charge. So here we have two charges, and then we want to consider the E field at point P. So as we have mentioned before, if we have multiple charges, then we can calculate the E field generated by each of the charge separately, and then we add them together. And of course, in the z-axis, we don't need to decomposite the E field so that it will be easy to calculate. That's why, for example, if you consider the point P prime out of the z-axis, then of course, from the positive charge, it will generate the E field like this, and from the negative charge, it will generate the E field like this. So they are not on the same axis, then you need to decompose it maybe Yeah, so you should need to decompose it into this axis and this axis, and then you add it up, then it will be very complicated. So that's why we consider the E field on the z-axis. Okay, so the derivation is not difficult. Okay, so for the E plus means the E field generated by the positive Q charge, and so it is K times Q over R plus square. R plus means the distance from the positive charge to point P. So this is R plus. So this is R plus. And similarly, E minus is a K times Q over R minus square. So R minus is from the negative charge to the point P. So it is slightly different. Of course, the difference are not too much, but up to this point, we need to distinguish these two distance. Otherwise, if you just approximate this R plus and R minus to be Z, then these two terms are actually the same. Then it just cancel everything. You end up to be a zero. So far, we need to distinguish between R plus and R minus. And of course, we can simply determine that for the positive charge, it generates the E field pointing upward. And for negative charge, we generate the E field pointing downward towards the negative charge and from the positive charge. So E plus pointing upward, E minus pointing downward. So the amplitude of the total E will have a subtraction here. Okay. So here we try to substitute R plus and R minus. So it is some simple geometry. So this is Z, this is the middle point. So this is nothing but D over 2. Sorry, D over 2. This is also D over 2. Okay, so in this case, R plus equals Z minus minus D over 2. So R plus equals Z minus D over 2. And similarly, R minus equals, this is Z plus D over 2. So we substitute R plus R minus to be in terms of Z and D. Okay, so next we try to, factor out the Z, factor out Z. So out of this square, so we have Z square here, and then here we need to divide by Z for the denominator. Okay, so we have Z over Z is 1, and then we have D over 2 over Z, which is a D over 2Z. And then similarly, this one is 1 plus D over 2Z. So nothing special, some algebraic calculation. Okay, so here we try to subtract them, so we need to multiply the common denominator. Okay, so we have this term multiplied by this term is the common denominator, and then in the numerator we have this one subtracting this one. Okay, which means that in the numerator it should be 1 plus D over 2Z square minus 1 minus D over 2Z quantity square. So this is A plus B square, which is A square plus 2AB, which is D over Z, and then plus D square over 4Z square. And then here we have a minus 1 plus D over Z, and then minus D square over 4Z square, like this. So we can cancel some of the terms, like 1 minus 1, and then this term minus this term. So we end up to be 2D over Z, 2D over Z to be here. Okay, so now we try to apply the Z is much larger than D, so that this term and this term will tend to 0. So we try to simplify this expression, and then we try to substitute this condition into this expression rather than substituting it here. If we substituting it here, then it turns out to be a 0. Then it doesn't make any sense. But after we do some simplification and then we try to applying this far field condition here, then it ends up this is 0, this is 0. So in the denominator, it is 1 times 1. So it ends up to be 2 times k. K is here. You can see this is k, and then this 2 is here, and then q, and then d is here, and then this is over z, and then this is c squared. So it ends up to be c cubed like this. So this is the closed form expression when we consider the far field. If we don't consider the far field expression, the expression will look like this, not so good looking, not so nice. Yeah, so we add this far field condition to make the expression nicer. Okay, so, and of course, just now we define the dipole moment P equals QD. So you can express it like this: K times 2P over C cubed. This is K times 2P over C cubed. Of course, this equation is written in the vector form, so E is the vector, and then P is the vector, and other terms are positive value because K is positive, Z cubed is positive, so E has the same direction as P. Okay. Okay, so far any questions? Okay, no question, I think. So we move on. So this part will be a more challenging part because we need to use the calculus. We need to do some integration to really calculate the E field. Yeah. So actually, because before this slide, we talk about when we need to consider the E field generated by multiple charged particles, then we can calculate the E field one by one, and then we add them together. But for some structure, the charge are not discrete charge. For example, in this page, we have the line of charge. This is a ring, and then we have charges distributed continuously. So then you cannot count, oh, this is a single charge, there is another single charge. This is the charge are distributed uniformly or continuously, so you cannot count it one by one. It is like, of course, it is not infinite amount of charge, but yeah, you cannot really count it one by one. So in this sense, we need to use the calculus. We need to try to separate into small packets and then try to add them together using the Riemann sum. So it ends up to be a integration. Okay, so here it says the equation for the E field set up by a particle does not apply to an extended object with charge, which means it has a continuous charge distribution. Then we cannot count it one by one. Okay, so to find the electric field, we consider the E field set up by a charge element, dq in the object. So where the element is small enough for us to apply the equation for a particle, then we sum via integration. Yeah, to the component of the electric field dE. So we try to separate into small packet. And then we consider a small packet as a single charge. Then we try to calculate the dE, the small amount of E field generated by this small packet. So we have many DE, and then we try to add them together. And then of course we add this DE, which is we actually need to use the integration, like the Riemann sum. Okay, so a ring of uniform positive charge, blah blah blah, differential element of charge occupies the length ds. Greatly exaggerate for clarity, and then this element set up the E field DE at point P. Okay, so of course for this question, we don't actually need to use calculus. We don't actually need to use integration. And after finishing the derivation, you can see that it's just like integrating a constant, which is kind of stupid. But of course, this is the way to show you how to use the integration. I mean, for this case, we don't really need to use the integration, but for other case, you really need to use the integration. So this is the way to let you familiar with what we need to do. Okay, so let's jump into this derivation. Okay, so the first step is to cancel some of the components. Okay, so here it says, of course, in this question, we have a ring. We have a ring with a positive charge uniformly distributed on the ring. And then what we need to find is the E field on this z-axis, also the z-axis. But the definition somehow different from the previous one. For the previous one, we have the electric dipole, which means that we try to connect the negative charge and the positive charge, and then you try to extend it to be the z-axis. But here it is a ring, which means it is a circle. So the z-axis is defined as a line perpendicular to the plane of this ring. This is perpendicular to this ring, and then this z-axis goes through the center of this circle. So this is how we define the z-axis. And similar to the previous case, only the E field on this z-axis is easy to calculate. Other points are not easy to calculate. Maybe you can use the computer software to do so if you are interested. Okay, so here, as I mentioned, we try to separate the ring into many small parts. Okay, so ds means the length of this part. And then we have charge dq. We have charge amount dq on this ds segment. Okay, so yeah, so it says the charge element on the opposite side of the ring, they both contribute field magnitude dE, but the field vector leans at the angle theta in the opposite direction from the vector from our first charge element. So it means that, of course, we try to have ds like this. And then this is a positive charge element because the whole ring has positive charge. And then considering this ds with dq, it will generate the E field at this point. And then pointing to that direction, you try to connect this one and the point P, and then you try to extend. So DE points to that direction. Okay, so this is not parallel to z-axis, but it's okay because this is a circle. So you can always find a symmetric part by connecting this point to here, and then connecting this point to here. So we can always find maybe this one called ds prime, maybe called ds prime. So for this part, it will generate the E field at point P pointing to that direction. You can try to connect that one. Okay, something like that. Okay, so because this charge amount should be the same as this one, because the length is the same, the density, the charge density will be the same. So dE, the magnitude of this one, maybe you can call it dE prime, dE prime. The magnitude of this one and this one will be the same, and the angle should also be the same because yeah, these two triangle are actually the same as actually the same triangle. So these two angles should be the same. So in this case, we try to cut this plane to this figure. Okay, so you can see that DS generate at point, this is point P. This one is point P, and then this is DE, just mentioned. And then we may call this one DE prime to match with this one. Okay, as much as theta are the same, and the magnitude of DE and DE prime are also the same. So when we try to decompose it to z-axis, and maybe this one is x-axis, so the x-axis component will perfectly cancel each other. So these two will cancel each other. And for the z-axis component, they will add up. Okay. And of course, this is theta. So when we try to decompose it, the projection on the z-axis, this is dE times cosine of theta. And then, of course, this one is dE times sine of theta, but they point to the opposite direction and they cancel each other. So the first step is to canceling some of the components so that to simplify our calculation. If the x-axis component cannot cancel each other, then we need to integrating the different component one by one. Okay, and then it will make things complicated. That's why we are not able to calculate a point p prime out of the z-axis. It will make things very complicated. Okay, so yeah, so next, yeah, I think I have already mentioning it. So the component perpendicular to z-axis cancel, and the parallel component adds. Okay, so that's what I mentioned on this page. Okay, so the next thing is that just now we know dE equals I mean the DEC, the z-axis component should be dE cosine of theta. So we need to find what is cosine of theta because we would like to do some integration. And of course, theta is not a known variable because for this one, the known variable is the radius of the ring and then the z and then the z. So we'll try to express z in terms of, for example, r, z, and of course some other constant, rather than this r, small r, or theta. Okay, so here, cosine of theta, when we look at this figure, this is theta, and this is, of course, theta. And cosine of theta is like z, the adjacent sine over r. So we have z over r. And then we don't want to have r, small r, because r is not the known variable. The known variable is capital R and z. But according to Pythagorean theorem, we know small r squared is z squared plus capital R squared. So r is square root of a z squared plus capital R squared. Okay, so substituting to here. So z is the known variable, capital R is the known variable. So this is good. And of course, this is a square root. So we can write it as a half power. Okay, so this is cosine of theta. We will need to use it later. And then, so for here, the z-axis component is dE cosine theta. Okay, so dE will be 1 over 4 pi epsilon naught. This is k, because originally E is 1 over 4 pi epsilon naught times Q over R squared. R is the distance from the point we concern to the charge, and then this is the charge amount. Here we consider is dE, so we will have dE equals 1 over 4 pi epsilon naught, and then times dQ over R squared. Okay, so here dQ will be lambda ds. Here we define another variable called lambda, which is the linear charge density. Later we will also have a surface charge density or even volume charge density. So you need to care about whether it is linear or surface or whatever, because it is related to the SI unit. If it is linear, which means that we consider this ring is very thin, it doesn't have any thickness, so we consider it is a line rather than with some surface area. Okay, so in this case, we consider lambda to be a linear charge density. So which means that this is a ring, and you can consider it a circle. So the length of this ring is like a 2 pi r, 2 pi capital R is the length or the circumference of the circle. Okay, so this is the length. So it multiply. The length times the linear charge density. Linear charge density will be the total charge amount Q, something like this. Okay, or this is a small part, so we will have ds multiplied by lambda will be the charge amount on that part, because we assume the charge is uniform. So yeah, it is something like this. This is the total charge, then this is the total length. The total length multiplied by the linear charge density is the total charge. And this is a small segment, small length, and then multiplied by the same linear charge density will be the small charge amount on this segment. Okay, so here, this is actually dQ. As we show here. This is dQ. dQ is lambda ds. So we put lambda ds here, and then R squared. So this is dE. And then we have cosine theta. So we have cosine theta as this one. Okay, so dE cosine theta look like this. So complicated. And then, of course, this is R squared. R squared will be this one without the square root. So this is something like a c squared plus capital R squared. So, and then multiply by this half power. So it is 3 over 3 half power in total, like this. And then we try to put a ds at the back, and then we have lambda z lambda here. Okay, and all the other stuff are the same. So far it might look a bit complicated. Okay, so but here it is. So this is the expression for dE cosine theta. So it will generate here. Okay, so the next step is just to integrate for the whole ring, because just now we consider this a small segment, and then we try to integrate it over the whole ring. Then it will be the total E field generated by this ring on this point P. So dE cosine theta is this expression as in the last page, and then we, of course, this is ds is the length, so we integrate it from 0 to 2 pi r, like this. Okay, so here this is the looks like some stupid things is that this whole term is actually a constant to ds. You don't find any variable related to ds to the s. Or in other direction, it's like for every small part, it generated dE on this d-axis will actually be the same. So it's like you're integrating a constant. Integrating a constant is very easy. It's just like you're integrating a 4 dx from 1 to 5, something like that. Then it will be nothing but 4 times 5 minus 1, something like this. Or maybe it's like 4 times 1 5 dx. So it's like this is 4, this is also 4, like this. Okay, so this is nothing special. This is a constant. So we just put this constant here, and then we integrating the circumference of the circle. So it is nothing but 2 pi r. So we put 2 pi r here. And as I mentioned in the last page, we have 2 pi r times lambda equals q. So we have 2 pi r times lambda. So it will be q here. So finally, we have 1 over 4 pi epsilon naught times qz, and then over z squared plus r squared quantity to the 3/2 power. So this expression look a little bit complicated. And here we also apply the far-field condition. Okay, the far-field condition. Okay, so for this one, z doesn't necessarily to be much larger than capital R. But here, if z is much larger than capital R, then the expression will be simplifying like this. So which is almost the same as E equals K times Q over R squared, something like this. Okay. Almost looking the same, unless except small r is written as d. Okay, so these two are looking almost the same. And why it will be like that? Because if z is much larger than r, then in this expression we can simply ignoring this one. Ignoring this one means we have z squared to the 3/2 power, which means it turns out to be z cubed. So this one will turn into c cubed, and c cubed and this z will cancel. This one down to c squared. So it ends up to be 1 over 4 pi epsilon naught q over c squared, like this. So it is like here we have charge equally distributed on this ring. And then if you just consider this z-axis, it is like all the charge distribute at the center, and then it will generate the same E field on this z-axis. But of course, this z is far away enough to have this approximation. This is something like the approximation, because z needs to much larger than r to make this r square negligible. Okay, so this is the so this is the expression for the line of charge the E field generated by the line of charge, or more precisely generated by a circle ring. Okay, so let's have a 10 minutes break.